Okay, so proportional reasoning. Let's show you some symbology. And I will zoom this up so that you can see that a little bit better. There we go. Proportional reasoning. The symbol for proportionality sort of looks like a little fishy that you might have made in elementary school. Kind of looks like that. It's actually the Greek letter alpha, but it kind of looks like a little fishy. Put little wings on it, be a little eyeball. You don't have to be fancy. So proportional reasoning. So if I say that y is proportional to x, what that means in English is y is a multiple. Y is a multiple of x. So, as you're saying, you look at the powers. So what if I had y is proportional to x squared? How would I write these in math? Well, if y is a multiple of x, that's what proportional means, then I could just write y equals k times x, where k is whatever the multiple happens to be. Right? Like there's a 3 in front. Okay, there's a 3 in front. But if I still take x and double x, I still get twice as much y. If I cut x in half, I cut y in half. Right? Okay with that? So what happens on the y equals x squared? Well, the original one had a power, y power of 1, x power of 1. Now we've got y is a power of 1, but x is a power of 2. So, if we triple x, if we have x, if we double x, what happens to y on each of these? Is it the same or is it different? I'll give you a minute to write and think and look and all those things that we do. Any brave soul out there want to take a shot at what happens if we triple x in this case? What happens to the y value?
Which one?
The first one. We triple x. Is y tripled as well? That's a suggestion. Yeah.
Y stays the same because the exponent is 1, so 3 times 1 is still 1. Oh, wait, no.
Okay. He's going to rescind his argument about that. Yeah.
I mean, if you just think of the parent function, y equals x, all you're doing is adding, all you're doing is saying that x 3 times. So all of y.
What is 3x squared? 9x. So did we triple it? We tripled x because if x was 1, now I have x is 3. If x was 3, now I have x is 9. But there was another function out there, and the other function was squaring whatever you had for x. So if you tripled x, you actually tripled the value inside the square, which means my y value is now not 3 times bigger, but rather 9 times bigger. And that's tricky. That's something you don't do a lot in math, and you're probably not practiced a lot, so it's not, triple one with triple the other. Aren't they equal to each other? They're a multiple of, yes. But if there's powers involved, things are a little bit different there. So what's going to happen if we have x? Halve. I love how that's spelled. Halve. What happens when we have it? Yeah, go ahead.
Be a quarter of it?
It would now be a quarter. The new y value, so here the new y was 9 times bigger. Here the new y is going to be, the new y is going to be 1/4 x squared, so it's 1/4 of what it used to be. And so if we double x, now if we double x, y is going to be, the new y is 4 times the old y, if you like, because it's 4x squared. Now, almost every relationship in physics is one of 3 types. And in fact, take that back. One of 4 types, and then square roots occasionally. So, what happens if we have this? Y squared is proportional to x. Let's answer those same 3 questions. What will the new y be? Compared to what it was before, what's the new one doing? This one is trickier. The last one was kind of tricky because you probably haven't done that a lot. And you kind of had to stop and go, wait a second. Order of operations says I do the inside first and then I do the power. So how does this one work? Now the power of 2 is on the y instead of the x. Well, let's look. What happens when we do this? If I triple x, what was my original one? Y squared is a multiple of x. So normally y is square root of kx. If I solve for y, y is square root of kx. So now when I triple x, what do I get? The new y is the square root of 3 times the old y. It's only gone up by square root of 3. It's still a multiple. So my new y is square root of 3 times whatever my old y was. Y has increased by the square root of 3. Because y has a power of 2, but x only has a power of 1. And who are we controlling? We're controlling x, and then y is a result of the move. How we doing? Like, wake up and think, man. Come on, here we go. I've been up since 4.
Why?
Because that's when I work out in the morning. Except this morning it was 5:30. Huh? And then I go to bed at 11, right? Or 12. We're all built different, right? I'm just glad that everything in my body doesn't run that fast, because then you'd have heart problems and blood pressure problems and all those fun things. So, let's just say I don't suffer from insomnia. enjoy it, get more done. But anyway, so what happens if we now cut x in half? What's going to happen to the y? We cut x in half, so y gets cut by the square root of 2. Because we cut it in half, but the 2 is now under the square root when I solve for y. And last but not least, what happens if I double it? Double x, that is. If I double x, I get square root of 2 times the old y. So an awful lot of the AP test, when they actually have math, which I think, Nathan, you told me the year you took it, there were 3 questions maybe that you would consider math. Seems like that's been 2 years now, so.
There were not very many.
Yeah, and they were almost all like this. The ones that are like this, it's not actually calculate something, it's more like, hey, if I change this thing over here, what does that do to that guy? So if the powers are the same, the proportionality, whatever you do to one, you get to the other. But if the powers are different, you have to see which one got changed. So if we change the x's, we have to put that in the sort of in the parentheses of the power and figure that out. But if we change the y's, you're undoing the power, so it will be under a root of some sort, a cube root or a square root. Now, what are the main relationships in physics? Proportional to x squared, proportional to 1 over x, proportional to 1 over x squared. That's probably 99% of all the relationships in physics. The other 1% is a square root one. Period of a pendulum, period of a mass bobbing on a spring. The period questions are square root functions. They're their own Latin. Huh? Oh, yeah. So, let's see. So now, Newton's second law. Let's put this stuff all together. And then combine it with what we did yesterday. So, Newton's second law says sum of forces equals mass acceleration. So, the net force, sum of all forces, excess, unbalanced force. All of these words mean the same thing. Is equal to the mass of the object times the acceleration of the object. So, what is the net force? What is the sum of all forces? What is the excess or the unbalanced force? We use all those same terms sort of interchangeably on AP. So, somebody know the difference between their gross pay and their net pay? Because I know some of you have jobs and you know there's 2 different numbers on there for your salary, what you get paid. What's the gross salary? Anybody know? Yeah, go ahead.
Is it like the initial amount, like the total sum of everything that you get?
Right. It's the, hey, you're getting paid $9.25 an hour, you work this many hours, multiply those together, that's your gross salary. What's the net salary?
After taxes.
That's what happens after taxes, Social Security, fees, anything else. You're a waiter or waitress and you broke 3 glasses. Some little kid run out in front of you. It happens. Right? So, so your net pay is the extra, it's what you actually get to use, the usable amount, the take-home stuff. It always hurts my feelings because I see 25% of my paycheck go away. But Social Security, I pay for, so I'm glad I have it. It's like savings account for later. And then some of your taxes and stuff. I like having good roads and good schools and, things like that. But it is kind of weird because, like, when I pay taxes, they pay my salary back out of the taxes, right? So I kind of pay my own job, and it's like, why don't I just get to keep all of it? And, it's a thought. I've also tried to convince them to add a 0 at the end of my numbers, because what's a 0 between friends? 55,000 versus 550,000, just a 0. Nothing. Not even putting anything in there. Except for placeholder. Okay, so the net force is going to be mass times acceleration. So let's ask this. Force is proportional to what? Directly proportional to? Pick one of them. Because you only can have a proportionality between two variables. So I would agree that force is directly proportional to mass, because then acceleration is the multiplier. And force is also directly proportional to acceleration, because now mass would be the multiplier. The multiplier. What about mass and acceleration? So we got our formula as force equals mass times acceleration. So if I have more mass, it takes me more force to move you, right? Which is why you put your big, beefy, strong guys up in front of the football field on the line. You want them to push the other guys out of the way. And the more mass they have, the more force it takes to move them. And then they need to be strong because they have to move themselves. Okay? But if I also have the same mass and I want you to accelerate more, why does a bus not go from 0 to 60 in 4.7 seconds like a Lamborghini would? Because the mass is their thing, right? So if you want more acceleration, you have to have more force if you're talking about the same mass. So what happens if mass goes up? Let's leave force the same this time. What happens if mass goes up? What happens to the acceleration? So here, if I was to solve this for acceleration is force over mass. So one's in the numerator and one's in the denominator. So this would be, we would say these are inversely related. Inversely proportional. Huh? Oh, I've been doing it since I was 18. Like, I can read Greek quite well. I don't know what all the words are, though. I can read the language. If you gave me a Greek newspaper, I could pronounce all the words. I would not know what they said. I'm working on that. It's on the list of things to learn. The list of things to learn is like this big. And this is cutting into my learning new things time. With this, you're over here and I'm over there, and we're doing this at night and this thing over. Yeah. It's okay, though. Also cuts into my video game time. Such is life. Okay, so that's an inversely proportional, because if I apply the same force, if I push an object with some amount of force, if it's a big object, it accelerates just a little bit. If it's a small object, it accelerates a lot. So big mass actually goes with low acceleration if you push the same amount. For example, you know how we have the little kids come to our building? Let's say we had some really little kids come to our building and get their parents, right? And we had a kindergartner go screaming down the hall, because they're known to do that when they get excited, right? So screaming down the hall, and Miss Wilson goes out in the hall and grabs them. Stop that, right? I could do that. I could stick my arm out and catch a kindergartner and probably pick them off the ground, right? What if I tried to do that with a car?
It say no. It would disagree.
Well, I would apply the same force on the car as the car applied on me. The forces would be the same, but the accelerations would most definitely not. Car would probably keep moving, and I would have a detached arm. Or at least a really screwed up one. Right? If not worse. Little mangling. That's a good word. So, this proportionality, it's like another one that you might have run into in life is supply and demand. Right? If there's a little bitty supply, then the price point goes up. So small supply gives you, well, small supply and high demand gives you, you can sell it for this price. But if you have way too many of them and nobody wants them, then the price has to plunge so that you can get them off your hands. See the bakery items at the grocery store 3 days after they were made, right? They're all on that little table, like, hey, these are on sale. You're like, that's because they're stale. I know your ploys, oh grocery store. Okay, so do we have a feel about that? Okay, so now what did we add? Well, now, Newton's second law, we're going to have to write all the forces we have, add them together, and set them equal times mass times acceleration. So, let's start with a nice, easy one. And I'm going to turn the page so I have time. Okay. So, a book of mass 2 kilograms slides across the desktop with an acceleration of 1.5 meters per second squared. Meters per second per second. Yes, oh sorry. Yeah, it'd help if you could see that, right? What is the net force on the book? Now, this is a very simple problem that I'm about to make very complicated. Just because I can. No, not just because I can. I want you to see where we're going to go with easy things before we put hard things up there. What's the answer to that question?
3.
Force is mass times acceleration. 2 times 1.5 is 3. Okay. So, 3, the unit is the Newton. It's 3 kilograms meters per second squared. A kilogram meter per second squared is called a Newton because these are Newton's laws. Can we talk about what makes a law and what makes a theory?
It was in the...
I know it's on the notes, but have we talked about that? I don't think so. They're called Newton's laws because they tell you what is going to happen, not why it happens. Theories tell you why something happens, but not what happens. For example, if someday in the future Lauren gets married and has cute little children, will we know exactly what the children look like before they're born?
Yes.
We'll have an idea, right? We have a ballpark. But we don't know exactly what the offspring is going to look like because genes, right? The way they pair up, and recessive ones and all that kind of fun stuff, dominant ones, and then you got the epi thingies that express at different times depending on the chemicals in your body, and epigenetics. I'm not sure that's what it's called, but that's what it's epi something, but not EpiPen because that's allergies. This is not my field, even though they've tried to get me to teach AP Bio 3 different times in my career here at Blackman, and I've said, I don't want to, please, no. It doesn't have enough math. So, anyway, kids tend to be a little bit of a mix of their parents. genetically. They're definitely a mix of their parents. But visually, depending on recessive and all that kind of thing, dominant traits, the kid looks different. The theory of evolution tells you why the baby looks different, but they don't tell you what the baby will look like. So theories in science do not mean, I just think it might be true, but I don't believe you yet. If it got to be called a theory, we've proven it a lot of times. Okay? But it's telling me why something happens, not what happens. So we have a theory of probability that we use to do, like if you want to play poker, there are theories of probability that help you understand, like, this is more likely than that. And if I have these cards, I should do this thing because it helps me have a better chance to win. Yeah. So I had a kid several years ago that took my AP Stats class, and he took it because he said, I want to learn how to play poker so that I don't have to work the rest of my life. I can just play poker. And he was good.
Did it work?
Huh?
Did it work?
Well, unfortunately, I probably shouldn't have brought that up because it's a sad story. He graduated. He got a scholarship to Vanderbilt.
For what?
Super smart. He was going to go into math or science. He hadn't really decided exactly what. And he decided he hated Vanderbilt because of the rich kids there made him feel like a poor kid, even though I don't, Vanderbilt's every college, you find the college you fit into. You don't have to go to every one. There's one that'll fit you really well. And name brand is not the most important thing, at least not in my opinion. But he decided to come back here to go to MTSU where his friends were, and he could still get the undergraduate degree and then maybe go back to Vanderbilt to get his master's. And he decided he rode home with a guy that had been drinking. And the guy that had been drinking, of course, crashed the car, and he walked away from it, and Tyler did not. So that was very hard because he was only a sophomore in college, and it's like he was super bright, but he was also a lot of fun to be around. He was a really good kid, but just that one decision sometimes, right? It doesn't take but one to really mess you up, and so that's very unfortunate. I taught him and his brother. His brother was also really sharp, so that was hard. I've only ever lost 2 students that I've known, and it's been hard both times. There are a lot of things I'll do to you, for you, help you. The to you is give you quizzes and tests. I know you don't like those, but they're good for you. The helping you is how to fix it when you screw up those quizzes and tests and homeworks, right? So that when you take the test in May, it's like, boom, I got this. The one thing I won't be doing is going to your funeral, because I can't. I just can't. I had the other kid that died, I taught at Milton C. Christian. I taught his whole family. He was driving home to Auburntown one night, looked down to the floorboard and pulled off. You know how you, right? You look over there and you reach for something and you steer. And he steered a little bit off the road, and then he overcorrected, and it folded his truck right up into a tree. It went off the road and folded up to the tree. So I went to his graduation the weekend before on a Saturday, and his funeral was the very next Saturday. And as a Christian, it was devastating because he was planning to be a preacher. I'm like, Lord! I yelled at God a lot that day. And for a lot of days. God's big enough to handle it. It's okay if you don't believe in God. But I do. And you're going to hear it. But I'm not going to make you believe it. I'll just ask you to consider it. If you're a Christian and you don't know why you believe what you believe, I'll probably aggravate you too. Because I don't like that either. And I almost always pick the other side of the argument just to be contrary. So, there you go. So, on this problem, this is really simple, right? Because we're just doing the second law, and it's like force is mass times acceleration. Yeah? But what force? What forces have we learned? Well, free body diagram, if we're going to do this, what we got? See, I tell stories while I'm waiting for all of you to get caught up writing. So you're all done writing now, so we can keep going. Hey!
Do you have a jar key?
Do I have a...
Jar key.
Like
the, for the computer card with keys.
No, I don't.
I just figured I would ask you.
Yeah, I don't know where Bauman's is.
I don't know where it is either. I got the teacher, but I just figured I'd ask you.
And if she texted me on my phone is at my house, so...
There you go. I was like, sorry to interrupt, but I thought, well, I was like,
No.
let me ask Joy. She might know.
Yeah, I already tried to find it, and I don't know.
Okay.
So.
I thought, I was like, I'll go check with you before I moved on.
Yep, good thought.
You doing okay?
Yep. I still hate that one team. It still acts weird, so...
I sent it to them, and they said they're looking at what's going on.
Yeah, it's okay. we got it worked. I got it to work, but it always says this site won't load, and you have to click to go to the site, and then it opens up. I'm like, I just hate you. So, okay. All right. So, what forces do we have on this book? If we were to draw the free body diagram for the book in this situation, what would we put on it? Okay, so force due to gravity. Let's teach you that one. The force due to gravity is the mass of the object times gravity, which is the mass of the object is 2, and gravity is 9.8 meters per second squared. Although the AP test will let you use 10. Here's why. The only reason they do that is because they have to assume that some kids may not have a calculator that's working. And so 9.8 to multiply is tough, 10 is not. So they will allow you to use to 10, and I'm fine with either. Just be consistent. Okay. So, the weight of this object, which is the name for the force of gravity, it's another name for it, would be 19.6 newtons. You told me there was a normal force up. What force, how big would the normal force have to be? Why 19.6? It's not, the second law says if your forces are not equal, if your forces are not equal, you have to accelerate. So if I have a book sliding across the desk and one of those guys is bigger than the other guy, I would be shooting up in the air, I'd be sinking into the ground or sinking in the tabletop. We don't see that happen. So these two must be 19.6 newtons. Now, for sake of argument, let's just let the book go to the right. Do I know how it got moving? So I would call that a force applied, and our force applied would be 3 newtons. And what did I tell you about friction? We don't have friction unless they make me. That's it. Now, so it's easy to see who has to be the unbalanced force, right? It's kind of easy on the picture to see. So what you're going to be doing a lot of in the future is you're going to be drawing the free body diagrams and then figuring out the math that goes with it. That's where it gets a little tricky. Okay? Let's do, I'm going to set one up for you. And let's see if we can do this, and I'm going to let you work on it for a few minutes. A box is towed by a cable that makes a 60-degree angle with horizontal. If the box has a mass of 40 kilograms and an acceleration of 2 meters per second, what is the next net force? That's question number 1. Number 2 is, what is the tension in the rope? Okay. Trusty free body diagram. Force due to gravity down. And I'm going to go with the 10 this time, so it'll be 40 times 10, just to keep the numbers simple. This will be 400 newtons, because this is kilograms and this is meters per second squared. So we get kilograms, meters per second squared, which is called a Newton. Okay. We also have a force normal. that is not 400? Because you have a force tension that makes a 60-degree angle. So there is a part of the force tension that goes up, and there is the force normal that goes up. Do we see that? If I'm pulling on the rope, right, I've got a 60-degree angle, I'm pulling up and across. So now I have normal force from the ground up, but I also have a tension force up. Not the whole thing, but part of the tension pulls me up. Likewise, part of the tension does what? Part of the tension pulls me forward. So the net force is the tension part that is horizontal. Okay? And we know the tension part that is force horizontal. So this is what it's going to look like when I write the math. The sum of the forces horizontal. The way this gets read is the sum of, add up all the horizontal forces. Add up all the horizontal forces, and my object does what? It accelerates. What horizontal forces do I have? Force tension, cosine 60 degrees. And I'll wait right there because I know you probably need to look at that and write it and look at it some more and write it again. Or ask questions.
I looked down.
I know.
I understand.
Let's do what we're doing in geometry. Remember how they used to tell you to redraw the picture? Here's the force tension. Here's the horizontal part of the force tension. Here's the vertical part of the tension. And here's my angle of 60 degrees. So force tension horizontal over force tension would be adjacent over hypotenuse, which would be cosine of 60. So that's where I got that step. So the net force on the box, we know from over here, is 80 newtons. But we need to work with the other side to figure out what the tension in the rope is. So the tension in the rope, when I solve this, I get force tension X equals force tension times cosine of 60. We now know this number is 80 newtons, and the cosine of 60 is 1/2. So the force tension must be 160 newtons. Ooh, I could ask another question.
Please don't.
What's the normal force?
Oh.
Okay, let's back up and redraw what we've got. This would not be a free body diagram because you don't put numbers on a free body diagram. But, for argument, this is 400. We now know that this piece here is 80. What's that piece? Oh, this one's 160. So these are all the numbers we found. So what is this leg? How could we find this leg? We could either use trig or we could use the Pythagorean theorem. Okay, so 160 squared equals 80 squared plus y squared. Let's see, 25600, 6400, y squared. 16 squared. 250 squared, put 2 zeros, yeah. Yeah, that's one of my many skills, is I can do things like that really quick in my head for the most part. 256 divided by 64 would be, let's see, 128 would be 4 of them. So y equals, would be 40. Yeah, 40. And so this would be the square root of 40, which would be about 6.4. We probably should check that one. I'll probably check that one. And I got a calculator here. I'm going to say you probably get to it faster than I can get to it on my computer. Oh, too high. 6.3. 6.3. And we better check to make I got all my decimal places in the right spot too, because that doesn't seem right. Probably 63 instead of 6.3. See, this is 10,000s, this is thousands. Somebody check the math for me. 25,600. Check the 160 squared and divide it by the 80 squared. Make sure that I got my decimal places came out right. Should just be 4?
Yeah.
Okay.
160 squared divided by 80 squared.
So, oh, no. No, I'm an idiot. We're subtracting. We're not dividing. So, sorry about that, folks. 25,600 minus 6,400 equals y squared. So y squared is 800 difference, 19.2, 192. Oh, geez. Yeah. Say that again. 138. So 139. Just to keep in the same units we're in. Which means this one over here would have to be how much? So if we've got the tension piece pulls up with 139, what does the normal piece have to push up with? 400 minus 139, which would be 261. So now we know all of our forces and all of our parts of forces. Okay. I think I should let that stop and breathe.